This video is going to give a little overview of the gas laws. So first of all, when we think about gases, we usually think about them in a sort of simplified sense where we call them ideal gases. So about 95% of the questions you might see on the IB exam about the gas phase, you're going to be assuming that the gases are behaving in this sort of ideal, perfect, simplified manner. Occasionally, you will get a question about a real gas or deviations from ideal gas behavior. And then there are a couple small considerations that we'll do in a couple of lessons to talk about when gases might deviate from ideal behavior and why. But for now, unless it's specified that it's talking about a real gas or a deviation, you should assume that gases are behaving in this idealized way. So in ideal gas behavior, gas particles themselves are considered to take up essentially zero volume compared to the overall volume that the gas takes up. Essentially what that means is that there is a ton of empty space in between gas particles. So much so, thousands and thousands of times more empty space than the actual size of the particles, that the size of the particle is considered to be non-significant at the very least, but essentially the volume is considered to be zero. So in this diagram, it doesn't even come close to represent the true distances between particles. If these dots are gas particles, there's so much empty space between them that it's like the gas particles themselves take up almost no space. We're also going to assume for ideal behavior that gas particles experience no attractions for other gas particles. So when they bounce into each other, they have elastic collisions and there's no energy loss. Gas particles move in straight lines until they collide with things, and then they bounce off and move in straight lines again until they bounce off something else, and so on. And gas particles have an average kinetic energy that is proportional to their absolute temperature, their temperature in Kelvin. So this graph is a direct proportional relationship, just showing essentially that temperature is the same thing as average kinetic energy of particles. So when you increase something's temperature, you're increasing the kinetic energy, which means you're increasing the speed, because kinetic energy is the energy of motion. Now, that's the average speed. This is a graph we'll cover in more detail in later topics, but it's showing you that at any given temperature, like 300 Kelvin, 400 Kelvin, 500 Kelvin, there's actually a wide distribution of speeds. And while most particles are moving at close to the average speed, at any given temperature, you'll have some very fast particles and some very slow particles. And the shape of the curve changes a bit depending on the temperature that you're at. Another important concept to go over before we talk a lot about gases is pressure. And specifically, we'll get into gas pressure and atmospheric pressure. So pressure technically is just force divided by area. So for a gas, the force comes from all of the combined collisions of the gas particles with the surface of its container. So, if you imagine one person running into you, then a person is like a gigantic particle that applies a force on the area of you. Well, if you have gas particles, billions upon billions of gas particles colliding with you, although each particle is quite small, the combined force of all of those collisions spread out over an area creates gas pressure. So as we go through all these different gas laws, as we change conditions on a gas, and that if that change causes more collisions or more frequent collisions or more energy in the collisions, then there's going to, when they collide with the walls of the container, there's going to be more pressure for that gas. And so the reverse will hold true as well. If we decrease the number of collisions or the frequency of collisions, then we'll lower the pressure of that gas. So atmospheric pressure is something that we don't really think about. We're all under atmospheric pressure all the time when we're on planet Earth, and unless you're in a vacuum, like being in space. So we're always experiencing it, which is why we don't really notice it. It is our normal to be under a certain amount of pressure. And atmospheric pressure comes from all of the gas in the atmosphere sort of weighing down on you. But really, though, it's the collisions of the gas particles in the atmosphere. So if you are right at sea level, the atmosphere is densest there. There's the most gas particles at sea level. And so you have the most pressure when you're sort of at sea level. And if you were to go up a mountain or go up in an airplane, the higher you go, the further from Earth, the fewer and fewer gas particles there are in a given amount of space. And so there'd be less particles colliding with you, and that would translate to less pressure. So like when you blow up a balloon and it only takes a certain size, that's because the pressure on the outside, all these gas particles from the atmosphere are colliding with the outside of the balloon, and that's causing the balloon to get pushed back in. So the helium particles on the inside of the balloon are colliding with the inside of the balloon, trying to push it out. But the air particles like oxygen and nitrogen and carbon dioxide in the regular air on the outside are pushing back, colliding with the outside of the balloon. And so the balloon's always going to take a size where the pressure on the inside and the outside are equal. And so obviously there's a lot of things you can do to change how big a balloon is, but it's always at a given, setting of temperature and pressure, a balloon takes a certain size. It doesn't keep changing its volume. And that's because there's particles on the inside colliding, pushing out, and there's atmospheric particles on the outside colliding, pushing back. And atmospheric pressure pushes on the surface of everything. So on the surface of solids like you and me, but it also pushes on the surface of liquids. And so we'll see in class that if you fill a tube with liquid, the liquid will actually stay in the tube. And that's because the force down, there may be a force down from this liquid from gravity, right? Force of gravity is coming down, but the force of the air on the surface of the liquid is actually pushing back up and canceling out that force of gravity. And so the liquid column stays there. And this air pressure on the surface of liquids is actually what's going to be responsible for lots of different phenomena, but including how you're able to drink out of a straw. When you drink out of a straw, it's not really that you are sucking in, you're actually changing the pressure inside of your lungs, and the water is getting pushed in by the atmospheric pressure on the outside. So we'll talk about that a little bit more in class, but atmospheric pressure is an important concept to wrap your head around. Okay, a couple different gas laws to go over. First off, if we increase the pressure on a gas, which is what's happening from left to right, if we are increasing the pressure here, pushing down on a given amount of gas, all other things held constant, that will cause the volume to shrink. So as we increase the pressure of a gas, we shove it into a smaller amount of space. You can think about it as now that the gas particles are in the smaller volume, they would be colliding with the walls much more, and therefore this gas has a much greater pressure than this gas does. So if we increase pressure, we should decrease volume. And so that's what's known as an inverse relationship. So you want to write that in yourself right here. Pressure and volume of a fixed amount of gas at constant temperature are inversely proportional to each other. We'll have an equation for that in class, but essentially the greater the pressure exerted on the gas, the volume of the gas will decrease by the same factor that the pressure was increased. Sorry for the marker writing. So that is what an inverse relationship is. So what that means is if I double the pressure, then the volume should half. If I triple the pressure, then the volume should go down by a third or be divided by 3. If I half the pressure, then the volume should double, and so on. Charles's law is the next relationship. It has to do with what happens if you have a gas at constant pressure, a constant amount of gas. As you vary the temperature, what happens to volume? Well, as you warm up a gas, the particles move around more, and they therefore can push out with greater force. And so if the pressure remains constant, they will expand to fill up more space. So hot gases expand and cold gases shrink. Okay? So the relationship now is a direct one, that as we increase temperature of a gas, the volume will increase by the same factor. So if I take a temperature in Kelvin and I double that temperature, so from 200 Kelvin to 400 Kelvin, then the volume of a gas should actually double. It's not okay to just double the Celsius temperature. So 20 degrees Celsius, when you double that temperature, it's not 40 degrees Celsius. You have to first convert it to Kelvin, which would be 293. And then you would have to double that value to actually double the temperature and double the volume. The third relationship is temperature and pressure. If volume is held constant, so if this is like a locked jar Here, we've got gas particles inside this container. If I make the gas particles hotter using this Bunsen burner, they're going to move around faster and collide more frequently with the container walls. And that's going to increase the temperature, or increase the pressure. So increasing temperature, if volume is constant, increases the pressure of a gas. And that is called Gay-Lussac's law. And the final law, actually, we've already seen in class, which is called Avogadro's law. And that says that equal volumes of gas at the same temperature and pressure contain equal number of particles. In other words, the number of moles, or number of particles, and the volume of a gas at a constant temperature and pressure are directly proportional. So 2 moles compared to 3 moles compared to this many moles. So you should be able to see that if 3 moles takes up 30 liters, then 2 moles would take up 20 liters. And if we have 45 liters, then that should be 4.5 moles. So if you know about the volume of gases, then you also know about the number of particles of gas, because all gases, regardless of if they're helium, ammonia, oxygen, any gas, because those gas particles are surrounded by so much empty space, their individual volume, remember, is essentially non-existent, really not significant. And so it doesn't matter what the gas is. If you double the moles of a gas, you should also double the volume of the gas. That holds true for any gas. So that, once again, is a directly proportional relationship. The moles and the volume of a gas are directly proportional. So there's 4 main relationships to try to remember about gases: that pressure and volume are inversely proportional, temperature and volume are directly proportional, temperature and pressure are directly proportional, and the moles of a gas and the volume of a gas are directly proportional. And we'll cover the rest in class.